Look at this photograph of the aurora borealis. Those glowing ribbons are the visible signature of charged particles from space crashing into our atmosphere, stared directly toward the poles by Earth's magnetic field. We use that exact same steering mechanism in laboratories. Inside a mass spectrometer, a beam of glowing particles enters a dark chamber. As a magnetic field is applied, the heavier molecules take a wider path, while the lighter ones curve sharply, allowing us to sort them with extreme precision. Today, we are going to learn how to predict those paths. We'll move beyond guessing directions and master the right-hand rule to determine exactly where a particle will go, and use the magnitude formulas to calculate exactly how much force pushes it. By the end of this module, you'll see how these mathematical rules act as the underlying logic controlling massive natural phenomena and the precision tools of modern science. Let's look at this diagram of an open palm, representing the right-hand rule for force. Point your fingers toward the particle's velocity, v. Point your palm toward the magnetic field, b. Your thumb naturally extends to point in the direction of the resulting magnetic force, F. Note that this rule strictly applies to positive charges. Before starting an assignment, check your hand. It is very easy to use your left hand while holding a pencil. Look at these 6 cases. For negative charges, like electrons, you add 1 step. Apply the right-hand rule normally, but then reverse the direction your thumb points by exactly 180 degrees to find the true force direction. Now that we have the direction, we need the magnitude. The force, F, equals the charge, Q, times the speed, V, times the magnetic field strength, B, multiplied by the sine of the angle between the velocity and the field. Notice how the angle affects everything. If the charge moves parallel to the magnetic field lines, the angle is 0. If moving directly opposite, the angle is 180 degrees. Since the sine of both is 0, the particle experiences no magnetic force. So finding a magnetic force is always a 2-step process. Step 1, orient the spatial direction. Step 2, calculate the quantitative magnitude. This logic applies to a wire. An electrical current is just a stream of moving charges. So when determining direction, simply point your fingers in the direction of the current, I, instead of velocity. The magnitude formula adapts in a similar way. We swap out charge and velocity for current, I, and the length of the wire in the field, L. The equation becomes F equals ILB sine theta. Let's return to a single particle to see how this force shapes its path. Because the magnetic force is completely perpendicular to the velocity, it acts as a centripetal force, continuously pulling the direction into a perfect circle. We calculate the radius of that circle using the formula R equals mass times velocity divided by the absolute value of the charge times the magnetic field. Notice the relationship. If you increase the strength of the magnetic field, the circle gets tighter. This predictable, constant curving allows scientists to trap high-energy particles indefinitely within a confined space. Until now, we've put charges into existing fields. A current-carrying wire generates its own magnetic field. Look at this diagram. To find its direction, point your thumb in the direction of the current and let your fingers curl to map the circular magnetic field. To find the strength of that generated field at a specific distance, we use the formula B equals mu naught times the current divided by 2 pi times the radius from the wire. Let's put this into practice. Imagine a proton enters from the left, moving right at 2.0 times 10 to the 5th meters per second. The magnetic field is 0.5 teslas, pointing straight into the page. Step 1 is direction. Fingers point to the right with the velocity. The palm faces into the page with the field. Your thumb points up, meaning the magnetic force is pushing straight up. Step 2 is magnitude. We multiply the proton's charge by the velocity of 2.0 times 10 to the 5th and the 0.5 Tesla field. The angle is 90 degrees, so sine is 1. The resulting force is 1.6 times 10 to the negative 14 newtons. Since that force acts centripetally, let's find the radius of the circle the proton traces. We take the proton's mass times the velocity divided by the charge and the field strength. We plug in the exact values for each variable, and the final calculation gives us 0.00418 meters. Always state your units clearly. That physical radius represents exactly how tightly the proton loops. Because wires generate their own magnetic fields, they exert physical forces on each other. When currents flow in the same direction, the wires attract. If the currents flow in opposite directions, they repel. Look closely at this industrial motor. If you bend that wire into a continuous loop within a permanent magnetic field, the repelling and attracting forces on opposite sides push in opposite directions. This creates torque, transforming electrical current into rotational mechanical power. We have covered the critical mechanics. We've used the right-hand rule to find magnetic force directions, calculated their magnitudes, mapped out circular paths, and mapped fields from currents. Let's test your understanding. Question 1. When is the magnetic force on a moving charge exactly 0? Question 2. What single adjustment do you make to the right-hand rule for an electron? Question 3. If the magnetic field increases, what happens to the radius? If you know that the force is 0 when movement is parallel to the field, that negative charges reverse the direction of your thumb, and that a stronger field tightens the radius, you have mastered the mechanics. Understanding these precise interactions is exactly how we measure atomic masses in a lab and engineer the electric motors that drive our world.